PhD in geology from Texas A&M University and worked 20 plus years for Shell, Citgo, and Conoco. In 1995, he went to the DOE's Idaho National Laboratory. Starting in 2002, Dave spent about 14 years in and consulting with the Department of Homeland Security in risk assessment. He and his wife, Joanne, of 48 years, now live in Georgetown after their tours in Oklahoma, California, Idaho, New Mexico, and Washington, D.C. Both Dave and Joe are proud Aggies. His hobbies include cooking and woodworking, and he has been teaching adult education classes since 2009.
Okay, you're spotlighted, Dave.
Dave, it's up to you.
All right. Does everybody see it?
Yeah, yes. It's
Okay.
great.
Are we ready to go?
Yes.
Oh, we need to turn this off. Let's do that.
Looks great. Whoa.
Well, you're going to miss it.
Whoa. This is what we hope we don't see.
Okay, so I guess the first thing we ought to do is try to figure out what is an earthquake, actually. Well, it really is a type of acoustic energy, believe it or not. It results in a seismic wave, and that's what makes the ground move up and down. Now, what causes that is basically just two blocks of rock sliding past each other along a fault. And these things can happen very quickly and sometimes slowly. And we'll look at each of those as we work our way through. But the motion on faults is sort of a result of the real prime driver. And what is that? It's stress within the Earth's crust. Now, this is not emotional stress, this is the physical thing. So for you engineers out there, geoscientists like to deal with positive numbers, particularly us Aggies like positive numbers. And so we always have compressive stresses as positive. And that's only important as we get looking towards what that kind of thing actually does. So let's take a look at what the fault motions are. Okay, there's basically three kinds of faults, three motions that we use to classify faults. The first is what's called a normal fault. Can you see my cursor? Is that working out?
Yes.
And a normal fault, one side moves up, one side moves down. What's important about this is that it essentially is in a world where the Earth's crust is stretching. Like, the opposite of that, of course, is the reverse. The reverse of a normal fault is a reverse fault. This occurs where the Earth's crust is being shortened or compressed and pushed together. And then the third kind is a strike-slip fault. We also call them translational faults, where the motions are sort of side to side. There may or may not be much in the way of vertical movement on the faults, but the majority of the motion is lateral. Okay, those three types. The normal faults can be, but are often not seismic in nature, in other words, creating earthquakes. Reverse faults, I am not aware of any reverse faults of significance that are not seismic. They tend to be seismic, and you could probably think about why that might be true. Strike slip faults can be both. They can be seismic and they can be aseismic. Although the ones that we'll talk about today are the seismic variety. Seismic meaning earthquake causing. All right. I talked about hard and fast or slow and silent. When two bodies of rock slide past each other, first of all, we'll talk about the rocks themselves. The rocks might be what we call hard rocks. These would be rocks like granites or basalts, crystalline rocks, or limestones, or well-cemented sandstones, not soft and muddy like most of the rocks, for instance, on the Gulf Coast. Those we call soft rocks. When we have faults in hard rocks, they tend to, when they slip past each other, they tend to do it in jerks and pops, and those will happen quickly because there's a stress buildup and then there's sort of an instantaneous release of that stress. In the case of soft rocks, it's much slower. It tends to be slower because a lot more of the rock is actually being deformed. And you might think about it as being deformed sort of plastically, kind of stretching, all right? So it doesn't have that snap to it that you get in hard rocks. So I talk about hard and fast or slow and silent. This is some terminology. It's not particularly important. I just want to point out a couple of terms, though, that we'll talk about a little bit later. One is the epicenter. That's a term that most of you are familiar with. And an epicenter is simply the point on the surface of the Earth over which the actual faulting took place, all right? Because the faulting is happening somewhere at depth. And where it actually happens is this thing called the hypocenter. And if you want to try to keep them straight, think of your epi, right? That's epi, like epidermis, the surface of your skin, as opposed to hypodermic, right, is down underneath. So the hypocenter is the actual position of the fault where that break takes place. The epicenter is the projection up on the surface. Okay, now I told you that we'd be talking about stress, and it's important for a couple of different reasons. I'm showing you this to make 2 points in particular. First is that stress in the Earth varies from place to place. Now, what do I mean by that? If you look over here, what you see, these are called the principal stress axes. Don't let the terminology get in your way, but simply think that there is a maximum force shown here in red. There's a minimum, which is shown in blue, and then there's something in the middle called intermediate, which is yellow. Notice here, the maximum stress is vertical. And associated with that are normal faults, all right? This is important, normal faults associated with vertical stresses. In both of these other 2 cases, the maximum stress is horizontal, but the vertical component in one, the reverse fault, is the minimum, whereas in the strike slip, it's the intermediate. Again, these are important because it will determine the types of earthquakes that one will end up with. And we'll come back to this again later. Okay? Don't get too upset with it or don't get too wrapped up in it. It's a pretty simple thing to think about. But as I pointed out, this happens typically where the Earth is stretching. This happens where the Earth is being pushed together, the crust, and here is where it's sliding past each other. It's an easy way to think about it. Okay, a little bit of terminology here because I want you to be able to see where these things are in some real cases. It's not critical. Don't get wrapped up. But the part of the fault, this is a normal fault, what we call an extensional fault. There's the side of it that moves up is called the footwall. Why? Because if you think about it, kind of shaped like a foot. It's just that, geologists are not really into all that fancy, Latin, like the doctors and so forth. So we stick with things that are a little easier to remember. The hanging wall, that's the block that moves down because it kind of hangs over the footwall. So that's the two pieces. Now, let's just take a look at some of the real things. Okay, here's a normal fault, very nicely displayed. You can see that this black bed is offset. This is the foot wall. This is the hanging wall. So this block has moved down relative to that block. I use that term relative on purpose because often it's very difficult, especially with limited exposures, to know whether one block has moved absolutely up or absolutely down. But it's pretty easy to see whether they've moved relative to each other. So relative motions are what we typically tend to focus on. Absolute motions are a lot tougher to deal with. Here's something a much smaller scale. There's a pen for scale. And you'll notice there's a nice little normal fault there. There's your footwall, your hanging wall. But notice that there's another one right over here, and there's another one there, and there's another one here, and another one here, and another one here, and so forth. And it's not unusual, even at small scale, to see clusters of faults where the rock body is trying to adjust, in this particular case, to being stretched. Here's a slightly larger scale. This is out on the Pacific coast and some sediments in California. And these are reasonably soft sediments, by the way. But there's a really beautiful normal fault here. You can see this banded unit is offset very nicely here. You can see some more and so forth. Another thing I want to point out to you, however, is that not all faults are flat planes. But they're depicted that way typically in diagrams. But notice this one right here, it actually curves. And that's not unusual, okay? We see this often in diagrams, but there are many normal faults that actually do bend and actually become flat. I don't want to get into the details, the mechanics and all that nonsense, but these are not unusual. And in fact, this fault, this type fault that is curved is typical of the sort of thing that we see in the Gulf Coast. Okay, and sure enough, here we have one. This is the fault plane or the fault trace on the surface, runs right through that house. Notice the level line to the roof line here, that distance, and look at it over here. So this side of the house has clearly moved down relative to this side of the house. And you can almost see it in the warp on that front porch. Those of you that may have lived or traveled in Houston and can drive in some of the surface streets, some that come to mind are Gessner and Fondren and Westheimer and some of those, you can be driving along and you'll just feel yourself pop down or up depending on which way you're going. And there's typically a dark patch in the street. You've just driven across a fault. They're all aseismic faults. You don't hear earthquakes associated with them. And the rocks down there are only with a lot of tongue-in-cheek called rocks. It's really mud. All right, and those are aseismic. Now here's a couple of pretty well-known normal faults. I think those of you that have been in the Yellowstone Teton area should recognize the Teton Mountains. That's Grand Teton there. If you've been out on Route 40, out Interstate 40 to Albuquerque, you've gone through the Sandia Mountains, this is looking towards them from the west. This is looking towards the Tetons also from east to west. Both of these mountain ranges are fronted by normal faults. These are not, strictly speaking, this is a little piece of geology trivia for you. Neither of these mountain ranges are, technically speaking, part of the Rocky Mountains. Rocky Mountains were formed about 50 to 60 million years before these mountain ranges actually popped up. Both of them are due to large normal faults along the fronts. The displacements, just to give you a feeling for that, remember we talked about this being the footwall, the hanging wall was down here in the valley. Think of it as Jackson Hole, right? There's a reason it's a hole. It is because it's been thrown down. And it's somewhere on the order of 20 to 25, excuse me, 1,000 feet. So it's about 5 miles of vertical displacement that's occurred. A similar number here, I don't know the exact term, I'm sorry, the exact amount. I do remember when I was a student at University of New Mexico, they talked about a minimum of 15,000 feet. Now that mountain is at the very top is about 10,600 feet. So it's already, and this is about 5,000 feet. So it's about 5,000 feet of relief just from the top of the mountain to the valley floor, not to the top of that unit. That top of that unit is buried underneath about at least another 10,000 feet of gravel. Okay, enough for normal faults. Now we talk about reverse faults. Now here's a small reverse fault. This would be the footwall. This is the hanging wall. Here's the fault. Trace it right up through here. And here you can see that the hanging wall is sort of up and over the footwall. All right? So that's the difference. If this were a normal fault, this part would be below it, say this unit would be below that one, it would be down here somewhere. But this is a reverse fault. So we're talking about things getting squeezed together. Here's a group of them, steep. These happen to be quite steep, which is not unusual. But again, they can occur in clusters. They don't have to happen singly, which is the way we typically draw things anyway. Here's a much smaller scale. These beds right here are probably on the order of 1 inch or 2 inches thick. So that's a pretty small one, but it nonetheless demonstrates it quite well. Here's a road cut. This one's a bigger one. Here's the fault trace here. And this rust-colored bed is this rust-colored bed right here. So again, footwall up and over, hanging wall. Now, you'll notice in the title, I say it's reverse and thrust faults. Now, thrust faults are a special kind of reverse fault. They're special because they are very, very shallow dip. They're almost flat. And in fact, in some cases, they are. They literally are horizontal. They're typically associated with mountain building. All right, reverse faults on these small scales can occur for a lot of different reasons. Thrust faults are usually associated, associated with very large scale features. This particular one, this is up at Glacier Park, for those of you that have visited Glacier. By the way, if you have never visited there, put it on your bucket list, it's well worth it. You're driving around back up in here, and you're seeing all those beautiful colored rocks. These are all Precambrian rocks, about 1.3 billion years old, and they are sitting on top of Cretaceous rocks, which are only about 60 to 70 million years old. The distance that these rocks have moved is not precisely known, but the distance from here, this is Chief Mountain that sits out in front of it, okay, from here to there is about 15 miles. So we know that it's moved at least that far, and perhaps quite a bit further. I've heard estimates as high as 100 miles, although I find that a little difficult to swallow. And this is what you'd see if you were on the ground. This is Chief Mountain right here. These are 1.3 billion year old rocks, limestones in this case. There's the Lewis Fault. They're sitting on top of Cretaceous sandstones and shales. And this part is back here. So the distance from here to back there is on the order of about 15 miles. Thrust faults can be big earthquake producers, all right? And we'll see that here shortly. Now, strike slip faults. Ah, yes. If there are a granddaddy of all faults, strike slip faults have to have that honor. There are small ones to be sure, and you can read about them. You can look up strike slip faults on Google, and I'm sure it'll talk about some big ones and some small ones. But the big ones are the ones that sort of gather our attention. There's a little terminology here too. We talk about a fault being strike slip being either left lateral or right lateral. And again, geologists who like things keep things pretty simple. For the most part, the name simply comes from this. If you're walking along perpendicular to the fault and you have to turn left to find what it was you were following here, it's a left lateral. Similarly here, if you're walking along and you have to turn right, it's a right lateral fault. That matters because what that's telling you is the difference in the state of stress in the earth that created the fault. Now, these things can really wreak havoc. Here's a very small fault. This is California. This happens to be an offset of strawberry furrows, strawberry field, and these little guys are offset. Now, I can't tell you whether this one goes to that one or this one goes to that one just from here. But if you look back to this one, this is in an orchard. You can see here it is left lateral. You follow one of these rows of trees and you got to go to the left to get to that same row of trees. Here's some railroad tracks. Bill showed you a picture of some trolley tracks. Here's railroad tracks in California. Again, this is right lateral. So you're walking along the track and you got to turn right to get back to the track. Ah, yes. Here we are at the San Andreas. This is the one that sort of captures everybody's imagination, like in that little film clip I showed you at the beginning. These things can be huge, and that's why I talk about them being sort of the granddaddies of the faults. They tend to be fairly straight, although they do often have kinks in them, and we don't need to get into that in detail. It's probably more than you'd ever want to know. But the San Andreas out in California, okay, is in fact about, well, I can't give you exact length because it goes out to sea. We're not quite sure where it stops. But it's on the order of probably on the order of close to 1,000 miles long. It has a lot of sister faults. Let's put them, a lot of associated faults in California. But the one you typically hear about is the San Andreas. All right, but it is the one that is a plate bounding fault. What do I mean by that? It is the fault that has the Pacific tectonic plate on one side and the continental plate, the North American continental plate on the other. And you can even see that in California when you drive across it. And there it is, the San Andreas Fault showing entering your North American plate. So you're obviously driving to the east, wherever this sign was taken. Now, Bill was kind enough to send me a photograph this morning of this. This is a photograph that was taken by David Lynch. It's got to show the copyright there because that's important. And what he's showing here is this is the San Andreas Fault, which has the Pacific plate, which is the gray rocks, against the continental plate, North American continental plate, which are the tan rocks. Now, I wasn't there. I don't know where this outcrop is, so I can't tell you a whole lot about it. But one thing that makes me a little bit curious is how tame that appears to be. It looks like, you know, for moving a continent next to a continent, that's a pretty small potatoes looking fault. Okay. I have another photograph of the rocks in the fault zone itself, and this is what they look like. Now you can see in the fault itself, this is a fault zone. These aren't really perfect planes like a sheet of paper. Look at how tortured these rocks are. So there's a lot of squeezing and squishing that goes on in the faults. Some of this will create seismic activity and some of it won't. Now, let's leave faults for a while and talk about earthquakes themselves. So we talk about a bad earthquake or a not so bad earthquake. If we go back in time to about the mid-1880s, a fellow by the name of Mercalli is the first that sort of codified a scale for earthquakes, but it was a very qualitative scale. In other words, he would say it was a weak earthquake or it was a strong earthquake, or in some cases he would say, well, it was a very strong earthquake because it knocked chimneys over on houses. As an example. So if you do a little research into the Mercalli scale, you can see all sorts of interesting descriptions of how people tried to give people a feeling for how bad a particular earthquake was. Back in around 1905 or 1935 or so, Richter came up with a more quantitative scale, which is the one that we use today. The Richter scale, that's what you typically hear of. And it's a logarithmic scale. And what that means is that when you hear about a magnitude 6 earthquake, for instance, it's about 1,000 times stronger than a magnitude 3. Or to simplify it even further, an earthquake of magnitude 6 is 10 times stronger than a magnitude 5. As an example. Now, the Richter scale is more quantitative in the sense that what it's doing is it's characterizing the earthquake in two ways. Number one is the amplitude of the earthquake itself, and the second is the energy that is released in that earthquake. And you can see, as shown on the slide here, the amplitude may be a 10x, but the energy release is on the order of 32 times. Now, when we think about energy in the earth, and we're not talking about, solar energy or wind energy or oil and gas energy or coal energy, we're talking tectonic energy. This is the real deal, the big dude, as it were. And how big is that? Here's a diagram that I cabbaged off of a publication I found that talks about, this is the Richter scale over here on the left from 2 to 10. All right, and it talks about, and has some of the sort of the Mercalli descriptions along with it. Here are the actual numbers. The dates of the earthquakes are on this scale over here. Over on the right is an energy scale. So it gives you an idea how much energy. And let me give you a little example. The biggest earthquake ever recorded is the one that occurred back in 1960 in Chile, and it was on the order of 9.4 to 9.6, and that's huge. It had enough, it released more energy or enough energy to power the entire United States for 2,000 years. Now, I want you to think about that just a bit. The much more recent one that most of you probably recall back in 2011 is the Tohoku quake. This is the one that created the big tsunami in Japan that shut down the nuclear reactor and so forth and so on. Was quite a bit smaller. In fact, it's smaller by about an order of magnitude. And even the San Francisco earthquake, which we tend to think of as the big one, was even quite a bit smaller than that. So there have been a number of very large earthquakes, bigger than San Francisco. The San Francisco quake was quite equivalent to the energy that was released when Mount St. Helens blew its top. All right, now, what determines how destructive an earthquake can be? This has got to be something that most people are concerned about because that's sort of what you feel. This is what you hear, this is what you feel. So these are the various factors that will affect the destruction or the destruction capability of an earthquake. Obviously, the location. Where is it? How big is it? How deep is it? How deep is the hypocenter, for instance? How far you are, let's say, from the epicenter. What are the geologic conditions where you are? What are kinds of secondary effects that may be spun off from the earthquake? And then what is the architecture of where that quake has occurred? Now, some of these are more obvious than others, but I want to spend just a little bit of time on the architecture one. And I think you can see this when I talk through these next two slides, and then you think back to that opening clip, and you saw all those buildings falling down. When an earthquake happens, there's a variety. I mentioned that it sends out these seismic waves. Well, there's a variety of kinds of seismic waves. There's something called a P wave, or P for primary wave, all right? And it moves, all the seismic waves on these diagrams will move from left to right, right? And it moves through the Earth's crust in a series of compressions and what we call rarefactions. That is, it's like a spring. There's compressions and rarefactions. And when you were a kid, or when you're playing with your kids or your grandkids with a slinky, and you stretch it out and you stretch it and you compress it on one side, that's what you see, is you see that compressive wave moving back and forth. That's exactly how sound moves through the air and through the water, for that matter, okay? Another type of wave that is created when an earthquake happens is called an S wave or shear wave. All right, again, it's moving from left to right, and it's showing an up and down motion. Notice down here at the bottom, this shows what we call particle motion. Here it's back to front. Here it's up and down. So those are two what we call modes of motion. And obviously, it would be important to know that if you're building a building or a bridge. But earthquakes are more complicated than that. Here's something called a love wave, which is also generated by earthquakes. All right, and its motion is side to side. So it's like a transverse motion. All right. And you also notice that the motion is greatest at the surface and it decreases at depth. This is one type of what we call a surface wave. Another wave, surface wave, is called a Rayleigh wave. And if things weren't complicated enough, in this particular type, the particle motion is actually circular or elliptical, and is sort of an up and down, front and back. So I want you to think about that now that you're in this 35-story tall building and an earthquake comes blowing through, and you're going to get a P wave and a shear wave and a love wave and a Rayleigh wave. And there's no telling how that building is going to start wobbling around unless you've designed for it. And that's a very important thing for earthquake-proofing structures and building any kind of infrastructure in earthquake-prone areas. Now, I want to show you this, not to scare you. This is a seismograph, or seismogram, I should say. But what I want to show you here is a plot. What it is, it's just showing distance and time. So for those of you that are mathematicians, you know that the slope of that line, the steepness of that line, is the velocity, the speed of that wave. So you'll see here, P waves are the fastest. Those are what we call the first things that you'd feel, the first arrivals, all right? That's these guys. The shear waves are the ones in green. They come later, but they have a much higher amplitude. Then even later in time come the Love waves and the Rayleigh waves, all right? The amplitudes of these shear waves and even some of these waves can be significantly greater and typically are quite a bit greater than the P wave. So for those of you that have been in an earthquake, you may not have even felt the P wave, but you probably felt a shear wave, all right? And again, the amplitudes of these will depend on a lot of different things. One of which, I talked about geologic conditions. If you're sitting on, let's say, a granite, your house is built on granite up in the Colorado Rockies, you're going to feel that P wave. You'll feel this, but it isn't going to do much. If, on the other hand, your house is sitting in Houston and you have a big earthquake, the P wave will come rolling through. The S wave is going to take that nice soft sediment and make it wobble like a bowl full of jelly. And consequently, you get a lot of bouncing around it. Those kinds of things can be quite destructive. All right. The other thing is that people talk about aftershocks, and sometimes that could be the arrival of some of these later waves. Aftershocks do happen, but they're typically, what we talk about them is they are actually related to additional slip on the fault. So they are really separate earthquakes. But it's not unusual for them, for earthquakes in general, to occur sort of in packs, you know, series of them. So here's devastation. I mean, we don't need to spend a lot of time on this. A classic example of the '06 earthquake in San Francisco, Loma Prieta, a fairly recent one in California. In 1971, my wife was up at 6 o'clock when this one happened, and she watched the water in the swimming pool at her parents' home go back and forth and kind of slosh out on either end as the earthquake struck. This was before we were married. I was about 20 miles away and just getting up ready for work, and literally fell out of bed when it hit me. Devastation around the world. Yes, Mexico, Turkey, Puerto Rico, Haiti, Alaska, any number of places, Indonesia we could talk about. One of the things that you'll notice is the tremendous devastation. I tried to pick these to show. And again, it comes back to the architecture to a large degree of many of these places. Obviously, these were never built to be, quote, earthquake proof. These are just houses that were thrown up, most of them made out of cinder block, a fairly rigid material. It doesn't sway, and when the earth does, the cinder block breaks. I think some of you can recall there was not long ago, and I don't remember the year, there was a significant life loss earthquake in Italy. Again, very old buildings that were hundreds of years old were brought to the ground. Now, we see all this devastation and we think about the effects, obviously, on the people there of that location. But let me stretch your mind just a little bit, and I give you an example of how far-reaching effects can be, not only in space, but also into things that maybe you wouldn't necessarily associate with what goes on when a big earthquake hits. Back in 1755, there was a very large earthquake on the order of 8.5 to 9. Offshore Lisbon destroyed in that earthquake, partly by the earthquake, partly by a tsunami that followed it. And according to one writer, that country literally in the snap of a finger lost about 1/3 to 1/2 of its gross domestic product. Now, what does that have to do with anything? Well, what it has to do is that loss shifted the balance of economic power in Europe away from Portugal to Britain and France. And Portugal never recovered its economic preeminence in the world. Remember, they were a great marine power long before Britain was. Okay. If we talk about hotspots, where are all the earthquakes happening? Well, we go down to the Southwest Pacific. That's always a great place to go. There's a bunch of different things happening here, and I'll just try to point out a few of them. The colored dots, the colors, the scale you can see over here, yellow are 6 to 6.9, going up through orange, 7, red is 9, black is 9 and greater. So you see one black one here. We'll come back and talk about that here in a minute, but you can just see the enormous number. This is over a little over 120 years period of time. And look at that. I mean, they're just like, where would you ever go that there wasn't an earthquake down there? This, excuse me, this little map over here just is a map of where some of the larger ones, these are all greater than 8.3, I think it says. So dating back to 1797, 1861, and then as recently only here is only 2007. If we were to put the Banda Aceh earthquake, which has occurred up in here, which was in what, 2011, I believe. And then here's a seismogram again. I don't know exactly where this one came from, and there's a lot of stuff on there that's not important, other than the fact that you see a very clean P wave, giant S wave, and then you start picking up these other guys back in here, the Loves and the Rayleigh waves, and so forth. Now, why do we have so much going on in one place? Well, there's a reason for that. Excuse me, and we'll get into it here. So here's a map. There's showing Japan. Is this kind of hidden behind a lot of the red dots and yellow triangles? Yellow triangles are volcanoes. Red dots are earthquakes. But the important thing to look at here is this blue line. It has little teeth on it. You see those little teeth? Well, that is a geologist's symbol for a thrust fault. And what you have here is sort of what's called a megathrust. This is the Pacific Plate. If I can get my cursor back, the Pacific Plate here is being thrust under Japan. These volcanoes are the result of the melting of that plate at depth and coming back up through the crust. So this forms a megathrust, but it's also along a trench, an oceanic trench. It's called the Japan Trench here. There's a couple of other ancillary trenches, and it's not good enough for Japan to only have one. They've also got the Nankai Trough, which is another trench here, and it's also called the Ryukyu Trench on down here. And you'll notice another trench forming. This is actually part of the Philippine system, pointed the other way. Okay, so the plate motions here are quite complicated, but all of them are plate motions that are going to give rise to earthquakes. And where they have earthquakes like this, you get these guys, tsunamis. Can you imagine if you were sitting in a west-facing, or I'm sorry, an east-facing picture window in this tall hotel, okay, looking eye to eye to that tsunami coming right at you. Tsunami travel around 400 miles an hour in the open ocean. You're not going to outrun one. And they typically come in several waves. They're not a single one. It's kind of like dropping a pebble in a pond. You don't have just one wave, you get a series of them. So this is a view sort of along the beach, and this is if you were up at an elevation and watching the tsunami coming into the city itself. And this is from the Fukushima Tohoku earthquake, which is the one that inundated the nuclear power facility. Now, as I mentioned, sometimes these things have far-reaching effects that we really don't think about. And one of the ones that this one had, it strings together a number of different things. So it flooded the nuclear power plant, which obviously made them shut that down. But the lesson, one of the lessons that was taken from that was by Germany. And Germany said, well, you know what, we're going to shut down all of our nuclear power plants. This is just it's just not good for us. It's too dangerous. And we could argue that point some other day. But what they did is by shutting them down, they said, we're going to run all of our power generation off of Russian natural gas, which required a couple of things. Number one, it required new pipelines, which are geopolitically sometimes very difficult to install because you're crossing various countries' boundaries. But it also, because now 50 to 75% of Germany's power, gas, comes from Russia, they are extremely dependent on Russia for their electricity. Now, this didn't go down well with all the other members of the European Union. So there has been some pushing and shoving going on at the geopolitical level that is now considered in some cases a national security issue by some of those countries, all driven by a tsunami in Japan. So here we are on the other side of the world dealing with geopolitics that were created by a tsunami, 12,000, 15,000 miles away. Another look, this is a computer model of the tsunami and the propagation of the tsunami. This is the island of Sumatra. The actual Banda Aceh earthquake occurred about this point. It's hard to tell with all these dots on there. This particular record says 165,000 deaths. I've heard numbers up to 200,000. They're talking about a maximum run-up height. This would be the height of the tsunami as it came onto the shore, was on the order of 50 meters, 51 meters, which is about 150 feet. So you can imagine what that must have been like for the poor folks. And by the way, Banda Aceh, the island, that part of the island itself, you know, most of it is less than a few hundred feet above sea level. So you're not getting away. I mean, it is going to clean everybody's clock. So, and you can see that the tsunami is propagated literally thousands of miles away, all the way, and was felt and measured actually in coastal Africa. So what's driving all this? Well, I kind of gave it away a little bit, but here we have, in this case, and this is just a cartoon, a fault line of a reverse fault occurring. These are crustal faults. These are big faults, all right? Literally lifts the ocean. Well, we know that water doesn't like to form hills, right? It always seeks its own level. So some of this is going to go that way and some of it's going to go that way. And the stuff that goes to the coast, it's going to go and climb the coast until the whole thing sort of settles down. This is a cartoon of what you would see if you were to draw a cross section. And this could be the Japan Trench. It could be the Peruvian Trench. It could be the Alaskan Trench. There are trenches all over the place, and these are not uncommon, and they are typically, these are large megathrusts and will result in earthquakes. And so we look at a map of the Earth. Here's the classic ring of fire, as we call it. These red lines are oceanic trenches, and you can see where they are. This is a big mess, and by the way, there's a lot of smaller stuff in here that you don't even see. And you'll notice some of them here are where the plate is, this is moving north, overriding that plate. This plate is moving west, and west undergoing and undergoing the Asian plate, the continental plate. The yellow dots are just earthquake activities. And you can see this takes it all the way around. And there are actually some convergences that are going on now. Africa is running into Europe, Mediterranean. You better take that cruise quickly because someday it won't be there. But actually, it'll sort of always be there in our lifetime anyway. Now, that's all the natural stuff. We're running out of time here. I want to run through this last pretty quickly. Can man induce earthquakes? And the answer is yes, we can. I don't want to get into all the variety of ways that it can be done. There's more than one. But the thing that's been in the news most recently about earthquakes being caused by man has to do with fluid injection. This is a cartoon, by the way, of a geothermal energy system where they pump cold water down. You get the fluids move across, then you pump the hot water. It gets heated up down here, pumped up the hot water, it flashes the steam, and the steam runs a turbine and you create electricity. That's how the geothermal systems work. Well, this business about pumping water into the ground has been related and is part of the operations called fracking. And so back in 2000, what was it, 11, I guess, in Oklahoma, there was a 5.7 earthquake, and people are going, this is crazy. This is Oklahoma. This is the middle of the continent. How are we having an earthquake? Well, there was fracking going on, and the fracking was, in fact, associated, the earthquakes were associated not with the fracking itself, the fracking activity, but rather the injection of wastewater into wastewater wells that were some distance away, and modifying the injected water actually modifies the stress state and allowed slippage to occur. Similarly in Ohio, same kind of thing happened. There it actually activated what was previously a previously unknown fault. So yes, man can create these things. Where it happens is very much determining by the state of stress of the earth. And that's why it's important to know it. Now, what I want to do here is show you a little cartoon, and we're going to do a little thought experiment. What I want you to think about is pushing a box, a heavy box, or trying to push a heavy box up a ramp. That's what we've got here, a little box. We're going to try to push it up that ramp. But it's really, really heavy, and we push as hard as we can, and we're not getting anywhere. And the reasons are pretty simple, is that the stress, the force on that box is too great to overcome the slippage, that T. All right? But now your friend comes along and takes about half of that weight out of that box, and sure enough, you can go ahead and push it up the ramp. Well, in effect, not mechanically, but in effect, that's exactly what's going on by injecting wastewater, injecting water at high rates into the earth, is you literally modify the state of stress, you reduce the normal stress, and you will allow slippage to occur if the state of stress is such that it will promote slippage. So you don't always know that. So it's important to know the state of stress. And let's take a look at Texas. So this is a compilation of a whole lot of work that's been done for Texas, Oklahoma, and its surrounding areas, where you see the cool colors, the blues. Here, the state of stress is such that you would promote normal faulting. That means that and we know this because you saw that slide, that the maximum stress is vertical. So what's happening is that Texas, in effect, is getting longer in this direction. Okay, this is the Rio Grande Rift. It's getting wider, right? In the warmer colors, this is where we have the compressive stresses being in the horizontal, where we may be creating reverse faults or strike slip faults. And that's what this little scale down here is telling you. Okay, with that, I want to throw up a couple of, or a few URLs that you can go to. This is, I think, going to be made available in Nature Notes or in some other form to you. And what I'd like to point out is a couple of things you can see about and read about seismic waves and everything and more that you want to know in Wikipedia. Bill Blodgett sent this to me. It's a great little movie. It's a video of motions on the San Andreas Fault. It's a computer model of that. This is a similar one that was done by the California Academy of Science. And I really want you to take a look at this particular site because it shows you where earthquakes are happening all over the world. It's essentially in real time. And if you were to click on that, if it was a hot link, it would take you to a map of the world, and you could click on Texas and see that at, I think it was 8:53 this morning, there was an earthquake of magnitude 2.5, 5 kilometers deep, 8 kilometers southwest of Falls City, Texas. And that's it. Do we have any questions?
Well, you know we do. And our first question is from Laura. She wants to know, why was Borneo free of
Great question.
Or what?
Great question. If you think about it, I don't want to run back to the slides, but maybe I can real quickly. Yeah, real quickly. We don't have any plate boundaries. It sits in the middle of a plate. Okay, these are not boundaries. These are continental, or I'm sorry, country boundaries, borders. So think of it like a cork, which is on a plate that is surrounded by other tectonic plates. So there's really not a whole lot going on Borneo itself. It's kind of like not a whole lot is going on in Oklahoma.
Great. Okay. And we have a question from someone named Sam. And it is, have any animals been trained to predict earthquakes in any useful sense?
I'm not sure that I can answer that definitively. I know that there have been studies going back at least 50 years that have tried to correlate certain behaviors, animal behaviors, with earthquakes. Birds and cattle are two that I know of where they have looked at behaviors where people feel like for whatever reason they sense something is coming. Actually, I think there was also a study on dogs, but I can't cite where that research is. I don't know that training, if we knew what it was that was causing that, if it's real, then maybe we could train them. But I'm not aware that anybody's ever done that.
And did Germany actually have any nuclear plants sitting near an active fault?
I don't know the answer to that. I don't know. I don't know of any particularly active faults in Germany. That's not one of our sort of hot spots, so to speak of. There have been nuclear plants near earthquake zones. Obviously, the Fukushima was one. It's easy to say now in retrospect that wasn't a very smart place to put one. There's also another one in the United States, the Diablo Canyon nuclear power plant, which is the only nuclear power plant still operating in the state of California, is located not far from the San Andreas Fault.
Wow.
And it, by the way, is in the process of being shut down.
Okay. Is an earthquake possible here in Georgetown?
Doing what?
Yes, we hope not. Is an earthquake possible here in Georgetown?
I would say that it's highly unlikely. I mean, you know, when you deal with the earth, kind of anything's possible, but if I had to put odds, I'd say about the chances are probably 1 in a billion that an earthquake would actually happen in Georgetown. That was a natural earthquake.
That sounds good. Well, where is Falls City, Texas? Is that where you said the earthquake was?
Well, funny you should ask, because, and I don't know if I can do this, Candy, but let me try to. I don't know if you can see. Can you see this screen now? Well, maybe not. Do I have to go back to share? Yes. Okay.
Yes. We're looking at the root cause of tsunami right now. Okay, now we're looking at,
You see this map?
yes, uh-huh.
Yes.
Okay, so that little blue dot is Fall City, Texas, believe it or not.
Oh, wow.
So it's not so far away. But let me zoom out. I'll just show you real quickly what you can do with this map. It's kind of fun to play with because it's, like I said, you can play with it. This is, you click on a particular, the size of the dot obviously is the size of the quake. But when you click on it, you come over here and it pops up this thing. It tells you that that one, the blue one, is a 6.0 earthquake. It occurred 3 kilometers east-southeast of Jaco, Costa Rica. There's the time and date and the depth. So all of that information is shown here. Or if you want to go cruising, we can cruise here and we can say, well, I like the look of this earthquake. And click on one over here and whoop, and up will pop, it'll turn blue. There's the one in Hawaii. It occurred today at noon, roughly noon 30, Hawaiian time. No, I'm sorry, Eastern time.
Great.
So this is a map you can move around the world, and you can see that there's been some activity out here in the Southwest Pacific. There's a pretty good sized one. That's a 6.1 off of Papua New Guinea. But again, this is a good map to answer. Go back to that Borneo question. These are the trenches. These are the subduction zones. And you see Borneo kind of sitting all by itself, sits out there on this, I don't know what it's called. I think it's called the Indonesian plate. I don't know the names of all the plates, but that's what I think what that one's called. And it sort of sits out there and it's surrounded by subduction zones.
Wow. Karen, one of our birding members, said she lives 70 miles from Mount St. Helens, and before it erupted, her cat tore into the house and hid under the bed for the rest of the day. So cats certainly do know ahead of time.
There you go. There you go. And there are, yeah, there are theories, and that's exactly what they're, just theories, that large earthquakes, large and including volcanic eruptions, are preceded by changes in the electromagnetic field of the Earth.
Wow.
Now, exactly how all that happens, I can't tell you. I'm not enough of an Earth physicist to tell you that, but I can understand that there are ways that certain animals probably can pick up on that, because it's, I think a lot of people believe that's literally how homing pigeons navigate, is by magnetic flow lines.
That's very interesting, Dave. We want to really thank you for this presentation. It's been great, and we certainly appreciate it. And we'll go back to Bill.